Yeah, thanks very much. Yeah, I think my talk follows on quite nicely from that question, so I'm quite pleased. So yeah, my name's Jason Sanders. I'm very pleased to be involved in these sort of anniversary celebrations of the IOA. I was here. I started a postdoc here 10 years ago. I'm very grateful to past members of the IOA. I'm going to talk, my work when I was at the IOA, and I've continued that, is on the evolution of the Milky Way. So we've heard some motivation for why we should study the Milky Way. It's the setting in which we understand many smaller scale astrophysical processes, and it's also our prototype galaxy for understanding galaxy evolution and kind of broader cosmological studies, both observational and simulation based. And when I started at the IOA in 2014, we'd just seen the successful launch of the Gaia satellite in late 2013, and we're eagerly anticipating data from that. And now we have all of this wonderful data, as we've already seen. So Gaia has provided us with nearly 2 billion position and velocity measurements. But I think, maybe one of the real powers and strengths of Gaia is its complementarity, the way it sort of completes other data sets, completes other surveys. And in particular, Gaia's combination with large-scale spectroscopic surveys, which have really boomed in the last 10, 20 years and continue to do so. So here's an example from recent work from Anna Kirosh, where there's a set of 10 million stars, where we have Gaia telling us something about the orbits of the stars in the galaxy, and then the spectroscopic surveys giving us metallicity and other more detailed abundances. But to be fair, Gaia itself is also providing lots of this wonderful information. One of the recent great data products from Gaia are these low-resolution BPRP spectra. And despite their low resolution, R of 50 to 100, many authors have demonstrated that you can still get good metallicity information from them. And together with my student, Connor Fallows, we've been exploring whether you can get even more detailed abundance information, maybe carbon, nitrogen information from molecular features in cooler stars. And I think Sarah Kane at the IOA also has a poster outside on this very topic. And these data sets are now 220 million potentially stars for which we have this information. Okay, so with this wonderful information, what are we trying to achieve? Well, my perspective is trying to, instead of sort of following the evolution of galaxies as we look back in redshift, can we instead in the Milky Way look at following the evolution of a single galaxy? And maybe one clear way of doing this is by assigning stellar ages. So that now gives us a kind of clock, a timeline for following the evolution of the galaxy. However, this is a very hard task, as emphasized in David Soderblom's review article from over 10 years ago. And largely it's because all ages are highly model-dependent quantities. Very few absolute age indicators exist. I think also another real issue is that most of the action in a galaxy's history is probably very early on. And this is where the age resolution just becomes very bad. So we have to have large samples of well-understood, well-calibrated ages. So there's three methods here I'm going to highlight for how we find stellar ages. So the first is, probably very aware, you can measure the age of clusters by looking at where the turnoff is. We can do this star by star using Gaia's parallaxes, provided we have spectroscopic metallicities to break certain degeneracies. As we move up the giant branch, one real kind of revolution here from spectroscopic surveys is that carbon and nitrogen measurements tell you something about the mass of a giant star because of its effect on the CNO equilibrium and also their strength of dredge up. And so that's a route into finding ages for giant stars. And as we move even further up, there's empirical evidence to suggest that pulsating asymptotic giant branch stars, so Mira variables, have a correlation between periods and ages. Again, all of these methods are highly model dependent, but we can mutually calibrate them. So Hanyuan Zhang, who's a PhD student here, has done this for Mira variable stars using by trying to fix the kinematics as a function of age for different groups of stars to make sure they're consistent. Okay, so using these three methods, I'm going to kind of illustrate what we can do, and I've organized the talk in a rather sort of crude and overly simplistic timeline, but yeah, the very first part of my timeline, Anchor has already very clearly addressed, so this early evolution of the Milky Way, the early spin-up of a small disk. And so the first stage I'm going to talk about is how do we know when the GSE merger event occurred? Together with Vasily, we looked at subgiant stars, main sequence turn-off stars, and we looked at whether there was an effect from the GSE merger and what the ages of the stars involved in this effect were. So we looked at this. Vasily found this population of kind of an in situ halo component, so a kind of a metal-rich population of stars that have near halo kinematics, so they're very slowly rotating. And if you look at the ages of these stars, you find that they're mostly old. And the idea here is that the youngest star in this population is then gives us the age of the merger event, because it's these stars that have been thrown out of the disk during the merger event. And it's this idea is well corroborated by simulations, as you can see on the right-hand panel, that these so-called splash stars only exist above certain ages. As we then go through in this galactic timeline, we need to be able to explain when the galactic bar formed. I think this topic of bar formation has received renewed interest in light of the results from JWST, in particular the finding of very high redshift barred galaxies. And also the realization that maybe the bar fraction is at sort of high-ish redshift is higher than previous HST results suggested. So the conditions are right in the early universe for bars to form. So yeah, and this nice example of even a bar at redshift 3 from Constantin. So yeah, very sort of high redshift bar. So how do we know when the Milky Way bar formed? So I took inspiration from a method that has been used in IFU studies, the Muse Timer project, where instead of looking at the bar stars themselves, we look at a component that only forms when the bar forms, and that's this nuclear stellar disk component. So this is illustrated here by the simulations from Barber and Kawata. If you look at the top panel here, this is the bar amplitude, the strength of the bar. The bottom panel is the star formation rate in the central region of the galaxy, so well within the bar. And as the bar forms, gas funnels towards the center, and star formation begins taking place in this component, in this central region, forming a nuclear stellar disk. So if we look at the oldest stars that are part of the nuclear stellar disk, this tells us when the bar formed. And here's a nice example of a nuclear disk from, I think, the FANGS project, JWST. So the Milky Way has a nuclear stellar disk. Here it is in de-reddened star counts. It's a very hard component to study because of the dust, the extinction. But we know it's about 10 to the 9 solar masses. It has a scale length of around 100 parsecs and a scale height of 30 parsecs. And its morphology is consistent with the disk, although potentially it could be a small bar. And to study this, we've been able to sort of complement Gaia in this high extinction region with VVV proper motion. So VVV is a ground-based infrared multi-epoch survey, providing us with proper motions that are highly competitive with Gaia and light curves. This region coincides with the central molecular zone. Now in this region, I've found a large sample of Mira variable stars. Remember from my various methods of finding stellar ages, Mira variables, they're bright stars, maybe good age indicators. And we can see that if we rank them in period, as we increase the period, so they're going to lower age Mira variables, that an NSD component, the nuclear stellar disk component, begins appearing. And in my very crude schematic, this corresponds to the nuclear stellar disk appearing at about an age of 8 billion years ago. So here's another representation where if you look at the blue line, this is the star formation history inferred for the NSD from the Mira variable stars. And interestingly, 8 billion years, 10 billion years, these two approximate ages for the GSE merger and the bar formation, maybe we could even link them together. And this was explored in Alex Merrow's work, where he looked at one Auriga simulation that has a GSE-like merger and showed that bar formation is basically produced by the GSE merger. And if you remove it, as shown in the bottom panel, the bar formation is delayed. So yeah, that's an interesting angle to pursue. And now just finally, I wanted to touch on this sort of final epoch of the history of the galaxy, what I've labeled as more kind of secular, quieter times in the evolution. So here we can use the third method I highlighted for age inference, the carbon and nitrogen measurements for the giant stars. And if you look at the metallicity as a function of radius for these giant stars, for the old giant stars, I should say, that there's a wide range of metallicity at each radius. And this means that either there's a bunch of stars visiting as they're going through on their kind of eccentric orbits in the galaxy, or stars have moved from their birth orbits to their current orbits. And that's a process known as radial migration, as illustrated in the right movie, where a series of transient, non-axisymmetric perturbations basically push stars around in the disk. And together with Nej Frank, we measured the impact of these two effects, the migration effect and the heating effect. And the migration effect is supremely dominant in terms of this dynamical invariance. And it basically acts like a diffusive process. Another nice product of this work is that we managed to measure the inside-out growth of the disk. So the older stars are much more compact and centrally concentrated than the younger stars, which are forming in a more extended disk. And this matches what's seen when you look at galaxies across redshift. Okay. So yeah, that's basically all I wanted to say. So we reached the kind of conclusion, how the Milky Way that we see today. I should just say, that the evolution is continuing in the Milky Way today, and I think we're going to hear about this from Dennis. So in particular, the Milky Way is being influenced by this series, or a couple of ongoing mergers, the Sagittarius dwarf galaxy, and also, perhaps more importantly, the Magellanic system, and that has an impact on inferences we make in the Milky Way. And then also the disk of the Milky Way appears to be wobbling, and maybe this is a result of this merger, these ongoing mergers from the Magellanic system, Sagittarius, etc. And yeah, together with a PhD student, we're trying to explore how we can extract this signal as we move across the disk using noisy Gaia data. So yeah, thanks everyone for listening, and I'll leave it there.
Brilliant. Thank you.